Let's start by revisiting the essence of postulate number 3 that we talked about, okay? So postulate number 3 basically tells us that it follows postulate number 2, which tells us that the only possible results of measurement of any observable are the eigenvalues, one of the eigenvalues of the operator corresponding to the observable, yes? So let's assume that there is some operator A, okay? And which can be diagonalized to give you some eigenvalues and some eigenvectors. Okay, so for definiteness, let us say that n equals 1, 2, 3. Okay, if you want, you can think of this as a 3 by 3 matrix. Now, since A is a Hermitian operator, the phi n's form a complete set or basis vectors in this three-dimensional linear vector space, right? So this should be obvious to you because we have explicitly shown this to be true. Okay, so now consider any vector which is the state vector of some particle in this Hilbert space, and I can always expand this vector as a linear combination of n equals 1 to 3, the eigenvectors of the, eigenvectors of the A operator, right? Now, if I measure A on this state psi, I am guaranteed one of three values, A1, A2, or A3, and the probability that I will get some value, one of these three, is equal to the overlap of phi m psi overlap quantity squared, right? And this is basically equal to the modulus square of the corresponding coefficient alpha m, okay? So if I write this out explicitly, this is phi 1, if alpha 1 phi 1 plus alpha 2 phi 2 plus alpha 3 phi 3, right? So for example, getting probability, the probability of getting eigenvalue A1 upon measurement of A in this state would be alpha 1 mod square and so on and so forth, right? That is what this postulate basically tells you. Okay, so now we want to revisit this postulate for a special case, and this special case that we will talk about is the case of an operator having a degenerate spectrum. Now, what is a degenerate spectrum? Well, thus far, we have sort of tacitly assumed that all the eigenvalues of the operator A or whatever operator that we're talking about are distinct, right? But this might not be the case. And there could be operators that have more than one eigenvalues the same, right? So this means that A operator has repeating eigenvalues. Okay, so then how do we calculate the probabilities? What is the corresponding eigenvectors? And how does this third postulate work in this particular case? This is what we want to address, at least in the first half of this lecture. And since this might not be immediately obvious, or you might not remember off the top of your head how to diagonalize such matrices, let us actually start with a very simple example, okay? So I'll start with an example. I'll take some matrix A, okay, which is equal to 0, 1, 1, 1, 0, 1, 1, 1, 0, okay? The reason I'm choosing this matrix A should be obvious once you find out what are the eigenvalues of this matrix A. So write down the characteristic equation A minus lambda I equal to 0, which for us would be minus lambda 1, 1, 1 minus lambda 1, 1, 1 minus lambda equal to 0. And if you work this out, you would actually find that the eigenvalues are given by the solutions to this equation, lambda plus 1 square times lambda minus 2 equal to 0. Okay. So what does this mean? So this is a 3 by 3 matrix, so it has 3 eigenvalues, but 2 of the eigenvalues are the same because it appears as a lambda plus 1 quantity squared, right? So there is 3 eigenvalues, lambda equals plus 2, minus 1, minus 1. And 2 of the eigenvalues are the same. Okay. So this is a degenerate spectrum because the eigenvalues repeat. And the number of times a specific eigenvalue repeats is called the degree of degeneracy. So number of times an eigenvalue repeats is called the degree of degeneracy. Okay. In this case, the degree of degeneracy of lambda equals 2 is just 1 because it only repeats 1 time. The degree of degeneracy of the eigenvalue minus 1 is 2 because lambda equals minus 1 occurs 2 times. Okay. So g of 2 is 1 and g of minus 1 is 2. G is the symbol associated for the degree of degeneracy. Okay. Now this is fair enough. This is straightforward enough. But the tricky part appears when we try to write down what are the eigenvectors of these corresponding to these 3 eigenvalues. Well, the eigenvector corresponding to lambda equals 2 is straightforward, right? How do you solve for this? You just plug it into the eigenvalue equation. A times x1 equals 2 times x1. And I will not prove this to you, but you can easily show that this equation A is basically 0, 1, 1, excuse me, 0, 1, 1, 1, 0, 1, 1, 1, 0, acting on some vector x1, x2, x3 equals 2 times x1, x2, x3. All of you know how to solve this equation. Go ahead and solve this equation and get the vector and normalize the vector. And the vector, the normalized vector, which you can easily show is this. This is the usual way of obtaining eigenvector, so there is no problem. Okay. But what do you do for the lambda equals minus 1 case? Well, remember that this is a 3 by 3 matrix. There is 3 eigenvalues. And there should also be 3 eigenvectors. So what is the 3 eigenvectors for the lambda equals minus 1 case? Again, solve for this. 0, 1, 1, 1, 0, 1, 1, 1, 0. Let's call this some alpha 1, alpha 2, alpha 3 equals minus alpha 1, alpha 2, alpha 3. Or if you rearrange this entire thing, you would actually get 1, 1, 1, alpha 1, alpha 2, alpha 3 equal to 0. So basically, you get only one equation. What is this equation? This equation is alpha 1 plus alpha 2 plus alpha 3 equal to 0. The 3 components of my eigenvector should satisfy the equation that if I simply add up the 3 components, it should be equal to 0. I only get one equation and I need to figure out 2 eigenvectors. So how do I figure this out? So if you remember your linear algebra course, you figured this out by simply guessing the eigenvectors. So I can easily guess one eigenvector. So all I know is that the eigenvector should lie in the plane corresponding to the equation alpha 1 plus alpha 2 plus alpha 3 equal to 0. So let me write down a vector that satisfies this property. So let me write some x2 vector, which is given by 1, 1, minus 2. Okay. Now why 1, 1, minus 2? Well, alpha 1 plus alpha 2 plus alpha 3 is basically 1 plus 1 minus 2, which is equal to 0. So the sum of the 3 components of this vector is equal to 0. So this is a perfectly logical vector to write. Now I can go ahead and normalize this vector. If I normalize this vector, I'll simply put a 1 over root 6 out front because that is the length of this vector. So hey presto, I have one eigenvector. But what is the other eigenvector? Remember that I have only one equation. So now I have 2 constraints to satisfy. I should guess another eigenvector that is 1 linearly independent of x2. In other words, I can always write down a third eigenvector that is given by something like 3, 3 minus 6. But this x3 and x2 are not linearly independent because x3 is simply 2 times x2, right? So I cannot claim that x3 is a linearly independent eigenvector, even though it satisfies equation A. Okay, I have written down one vector that satisfies equation A, but I simply cannot multiply this equation by 2 or 3 or 5.5 and write another vector that satisfies the exact same equation, because that vector will not be linearly independent of this vector. So I have two constraints to guess my second vector. That vector should be linearly independent of the first vector, and it should also satisfy constraint A. Should satisfy constraint A. Okay, so you can guess another vector that is linearly independent of this vector. I will guess the third vector. Something like this, -2, 1, 1. Okay. Now again, this is also something that satisfies constraint A, and you should check for yourself that x3 and x2 are linearly independent of each other. Okay. But now I have a third constraint. The third constraint is that it should be orthogonal to x2, because I'm dealing with the Hermitian matrix. So I better have 3 eigenvectors that are all mutually perpendicular to each other. This is a slightly easier constraint to satisfy. Obviously, x3 and x2 are not orthogonal to each other the way I have written them down, right? Because x3 transpose x2 would be -2, 1, 1 times 1, 1 minus 2, right? Which is -2 plus 1 minus 2, which is obviously not equal to 0. So they are not orthogonal to each other. But I know how to make them orthogonal to each other. I will simply use the Gram-Schmidt procedure. To make them orthogonal. Okay, what is the Gram-Schmidt procedure? Gram-Schmidt procedure tells you that if you have two vectors that are not orthogonal, take the first vector, normalize it, that's your first vector. Take the second vector and subtract off the amount of the second vector that is along the direction of the first vector. Okay, so in other words, I should take my second vector.
Excuse me, sir.
Yes, please.
सर वेटिंग रूम में अपने एक स्टूडेंट है, वेट कर रहा है सर.
नहीं, यहाँ पे दिख नहीं रहा है हमको, कोई नहीं है.
सचिन वो मैसेज करके बोल रहा है सर मुझे.
He is not in the waiting room because participant list मुझे यहाँ पे है. There is no Sachin. So ask him to log in and log off and log in again.
Yes, sir. Yes, sir.
So I will use the Gram-Schmidt procedure to make them orthogonal. Okay. Now, if I do that, what should I do? So I should make my first vector, which is x2, the way I've written it down. So x2 is 1 over root 6, 1, 1 minus 2. Okay. So now I will take my second vector and subtract off the amount of second vector that is along the direction of the, subtract the amount of the third vector that is along the direction of the second vector times the second vector. Okay. And then you go ahead and normalize this. If this looks a little confusing, go ahead and revise your Gram-Schmidt procedure, and you would see that this is actually quite straightforward. So if I do that, I will write down my normalized third vector, and you should satisfy yourself that this is true. 1, minus 1, 1, 0. Okay. This is an exercise for you, homework. check this. Okay, check that this is indeed true. Okay. So if I reuse the Gram-Schmidt procedure to construct the third vector, this is what I will get. So I have three vectors and three eigenvalues, lambda equals 2, -1, and -1. And I have three eigenvectors, x1, which is 1 over root 6. What was that? 1, 1, 1. Sorry, this is 1 over root 3. x2, which is 1 over root 6, 1, 1, minus 2. And x3, which is 1 over root 2, minus 1, 1, 0. Okay. Now you could go ahead and verify and satisfy yourselves that these three vectors are all normalized properly and are all orthogonal to each other. And this is how I will try to figure out the eigenvectors corresponding to a degenerate spectrum. So basically, up till now, what we have done is the following. Suppose if you have a matrix that has two eigenvalues common, the question is, how will you figure out the distinct eigenvectors corresponding to these degenerate eigenvalues? So we took an example, which is this matrix, okay? And then the eigenvalues for this matrix are 2, -1, -1. And for this matrix, the eigenvector corresponding to lambda equal to 2 is straightforward. By the usual method, you can get the eigenvector. But for lambda equal to -1, you have to figure out two eigenvectors that corresponds to the exact same eigenvalue. So you have only one equation. Okay, so well, I'll talk more about this symmetries and degeneracies degeneracies when I talk about symmetries. There is actually a very intimate connection between these two concepts. So when you work out the eigenvector for lambda equal to -1, you find that there is only one equation, which is basically what I would call constraint A. So I basically guessed an eigenvector that satisfies constraint A. Notice that this eigenvector is not unique. I can start with any eigenvector I want that satisfies constraint A. But once I have picked one eigenvector, now I should pick another vector in the same plane, in the plane A, specified by alpha1 plus alpha2 plus alpha3 equal to 0. That is orthogonal to the first vector and is linearly independent of the first vector and is also properly normalized. So the way you do this is you pick another vector that also satisfies this constraint A, that is linearly independent of x2, which is simple enough to do, which is what I've written down as x3 vector. Of course, x3 vector and x2 vector are not orthogonal to each other. So you use the Gram-Schmidt procedure to orthogonalize it. Okay, sometimes you can actually guess straight away a vector that is both orthogonal and linearly independent. If you can guess it, then well and good. You don't have to do this extra step. But if you cannot, as in this case, it's hard to guess something that is both linearly independent of x2 and also orthogonal to x2. So I simply wrote down a vector that is linearly independent of x2, which you should verify again. So check. This is linearly independent of x2. That's your homework. Okay. And then once you have used the Gram-Schmidt procedure to orthogonalize these two vectors, you have a set of three vectors, x1, x2, and x3. Among these, remember that x2 and x3 both satisfy constraint A. Okay. Now, let us actually demonstrate something that should be interesting to you. Let us prove that these are reasonable eigenvectors. These are a complete set of basis vectors for the given matrix. Remember that the given matrix is a Hermitian matrix. So these three vectors should form a complete basis. Of course, one way to verify that this is a complete basis is to prove that they are all normalized to unity and they're all orthogonal to each other, which is very straightforward to prove. But I will prove it to you in a slightly different fashion by showing you that they satisfy the completeness relation. What is the completeness relation? Remember that now I will switch to the Dirac bracket notation and I will call this guy x1 vector this guy is x2 vector, and this guy is x3 vector. And the completeness relation, if you remember, tells you that sigma I ei for all the basis vector is the identity operator, right? In this case, what is the left hand side? The left hand side is x1 x1 plus x2 x2 plus x3 x3 equals the identity operator. So I have to check whether this statement is true. Okay, I want to do this because I want to introduce you to the notion of outer product of two vectors. So I've told you that this combination is an operator, right? This combination of a ket times a bra. So let us actually verify how to multiply a ket and a bra. A bra and a ket multiplied is just a number. You know how to do that. It's just taking the transpose conjugate of the first vector times the column vector, and that gives you the number. But how do you use this? Let us take two vectors. Let us call the first vector, let us say x vector. So example or aside, let us take my x vector to be some x1, x2, x3, and let's take my y vector to be y1, y2, y3. Okay. The outer product of two vectors is x vector times y vector transpose. Okay, remember, x transpose y is just a number because that is a row vector times a column vector, but I am calculating column vector times a row vector. So this is called x1, x2, x3 times y1, y2, y3, and this is called the outer product of two vectors. Okay. Now, when I talk about angular momentum, I'll talk about this again when I talk about outer product of two vectors. Basically, outer product of two vectors, you can take them even if the two vectors live in two different Hilbert spaces. In other words, suppose if I have an x vector, so I'll come to this in just a second, but let's work this out. The way you would do the multiplication is, so a row vector times a column vector is a number, but a column vector like this times a row vector, this will be a matrix. What are the components of this matrix? The first component of this matrix is you take x1 and multiply it with y1, y2, and y3, and you form the first row. Okay, so this is equal to x1, y1, x1, y2, x1, y3. Now we take the second entry and multiply it by the elements of the second vector to form the second row. x2, y1, x2, y2, x2, y3. Then you take the third element and multiply it by the components of the row vector to form the third row. So this is x3, y1, x3, y2, x3, y3. Okay. So remember that these two vectors don't even have to have the same length to form the outer product. Suppose if my x vector were still x1, x2, and x2 and x3, and my y vector was just y1, y2, I can still form the outer product of these two vectors. I will use the exact same rule. I'll take the first element of the first vector and multiply it by the second one. So this would be x1, y1, x1, y2. The second row would be x2, y1, x2, y2. The third row would be x3, y1, x3, y2. Okay. This would be a 3 by 2 matrix, and so on and so forth. So this is the sense in which I say that if you multiply two vectors, if you take the outer product of two vectors, you can even take them from two different linear vector spaces. Okay, so this guy should put the x vector in my example belongs to a 3-dimensional linear vector space, and my y vector belongs to a 2-dimensional linear vector space. I can still take the outer product of these two vectors. These outer products would be very important in the theory of angular momentum, as I told you before, and we will revisit that in possibly the second semester of quantum mechanics course. So for now, let us go back to our original problem. We have these three vectors, and I want to compute x1, x1 plus x2, x2 plus x3, x3. And I want to verify that this is equal to the identity operator. I will do x1, x1, and then I will leave the rest of the stuff to you as a homework. So what is x1, x1? x1, x1 would be the column vector 1, 1, 1 times the row vector 1, 1, 1. So there is 2 factors of 1 over root 3. So I can write this as 1/3 column vector 1, 1, 1 times the row vector 1, 1, 1. And this is extremely simple because this is just 1/3. The first element is the first element of this guy multiplying all 3 elements of the second guy. So that will be 1, 1, 1, 1, 1, 1, 1, 1. Okay. This is my first outer product or first matrix. Okay, let me actually go ahead and do this. What is x2, x2? x2, x2 would be, there's 2 factors of 1 over root 6. So I will get 1/6, 1, 1 minus 2 times 1, 1 minus 2. So this is 1/6 times, I'll take the first element of the first vector, which is 1, and I'll multiply it through by all 3 elements of the second vector. So I'll get 1, 1 minus 2. Then I'll take the second element to form the second row, 1, 1 minus 2 again. And then the third element, multiplying every 3 elements of the second vector, will give me -2, -2, and +4. Okay, this would be x2, x2. And what will be x3, x3? x3, the way we have written it, is 1 over root 2 times -1, 1, 0. So this will be 1/2 -1, 1, 0 times -1, 1, 0. So if I work this out, this 3 by 3 matrix would be, I'll take -1 and multiply it through. So I'll get 1, -1, 0. The second row would be -1, 1, 0. The third row would be 0, 0, 0. Okay. So this is my equation number 1. This is my equation number 2. And this is my equation number 3. What happens if I add these 3 matrices? x1, x1 plus x2, x2 plus x3, x3. What's the first element? The first element would be 1/3 of this guy plus 1/6 plus 1/2. Okay, so I have 1/3 plus 1/6 plus 1/2, which is equal to, so I can write this as 2/6 plus 1/6 plus 3/6, which is 1, right? So the first element is just 1. The second element would be 1/3 plus 1/6 minus 1/2, which will be 0. You keep working it out and you get the identity operator in this 3 by 3 space. Again, don't take my word for it. Check this. Okay. So this is the sense in which you diagonalize a Hermitian matrix with degenerate eigenvalues. And of course, you don't have to prove that the eigenvectors form a complete basis using this procedure. You can simply show that they are orthogonal to each other and properly normalized. But I wanted to demonstrate this to you because it's a useful thing to know in quantum mechanics. Okay, because we've been using this notation thus far, you should at least know that there is nothing bizarre or strange about this. In the language of matrices, we are just dealing with matrices. That's all. Okay. So having gotten that example out of the way, and hopefully by now you know how to deal with degenerate eigenvalues and eigenvectors of degenerate eigenvalues, let us go ahead and understand how to calculate the probabilities. How does postulate 3 work? Okay, so let me switch gears now and let's talk about quantum mechanics. Okay, so let us say that I have an operator A. Okay, maybe this exact same operator A, this exact same operator A that has 3 eigenvalues. So A acting on phi n equals an phi n. Okay, and let us say that A1 equals to A3, sorry, A2 and A3 are both equal to -1. Yes, and I have 3 distinct eigenvectors, phi 1, phi 2, and phi 3. Now, how do I figure out this, the probability of finding A1? Well, the probability of finding A1 is still probability of finding A1. So suppose if I have a state vector of a particle, psi, I can again, in the usual sense, expand it in terms of the eigenvectors of this Hermitian matrix. Yes. Now, the probability of finding A1 is the exact same thing as before. Because A1 is not degenerate, there is only one value, one eigenvalue corresponding to 2. The probability of finding A1 is still the overlap of the phi 1 eigenvector with the state vector square, which is alpha 1 square, the same as before. But what is the probability of finding A2? Remember that the state phi 2 and the state phi 3 both have the same eigenvalue A3, -1, right? So what's the probability of finding -1? The probability of finding -1 is given by democratically the sum of both. The probability of finding A1 -1 is phi 2 psi quantity square plus phi 3 psi quantity square. Okay. In other words, the probability of finding the eigenvalue -1 is the sum of the probabilities that the state vector has an overlap with each of the degenerate eigenvectors. Okay, so in notational language, I can write this in the following fashion: P of an, the probability of finding an eigenvalue an is equal to I equals 1 to gn of alpha ni mod square. What does this mean? Gn again is the degree of degeneracy of the nth eigenvalue. Okay. So let us say that an has a degree of degeneracy 2. In this case, -1 has a degree of degeneracy 2. Then this is given by I sum over I equal to 1 to 2 of alpha ni square. So basically alpha n1 quantity square plus alpha n2 mod square, so on and so forth. Okay. So this is how the third postulate works in the case of degenerate spectrum. Okay, and I want to ask and answer a very important question at this stage. But before I do that, are there any questions about any of this? Any questions or any comments about this? Because I want to prove something important to you.
Hello, sir.
Yes.
Sir, these alpha 1, alpha 2, and alpha 3, can we like predict them before experiments, or are they like experimentally calculated values?
No. So this is an expansion of any vector in terms of the eigenvectors of any particular operator that you're interested in. These are not experimentally measured values. This is a theoretical input. Okay. Suppose if I'm interested in a different operator B that has eigenvectors, let us say beta 1, beta 2, beta 3, then I can write psi as an expansion in the other basis. Okay. So what I need to figure out is what is the state vector. Now, what freedom I have is I can always use a basis transformation, a change of basis, to write the state vector as a linear combination of the eigenvectors of whatever operator I'm interested in. Okay, so that I can always do. But to figure out what the state vector is, I have to solve what is called the Schrodinger equation, which we will come to in tomorrow's lecture, hopefully. Make sense?
Yes, sir.
Sir?
Yes, please.
So I couldn't understand the probability of finding -1 here.
Okay.
Say I didn't know the values of A1, A2 and A3. So as I wrote probability of A1 to be the magnitude square of the inner product of both the vectors. So if I do not know that A2 and A3 are equal, I can write them in the same way. So probability of A2 would just be the inner product and its magnitude square. But now when I know that the A1, A2 and A3 are similar, then I add them both. So how does this work? I cannot get that.
Okay. So remember that the first step in this, so this has stopped working. So I'll stop share and share again. Sorry about that. So remember that this program has a few steps. The first step is that you know exactly what operator you're interested in. In other words, you know exactly what is the matrix form of the operator that you are interested in. Now, it doesn't have to be a matrix form. It can also be a different form, like a differential form. But the proviso, the requirement for this program to work is that you know exactly everything you need to know about the operator. In other words, you know exactly what its eigenvalues are and what its eigenvectors are. Okay. So if you don't know that, you cannot answer any of these questions. That is the first statement. Okay. So in other words, if I want to measure an observable A, and I should know what is the matrix in quantum mechanics that corresponds to this observable A. Okay, and I should know how to diagonalize this matrix. I should know the eigenvectors and eigenvalues of this matrix. Now the second point is that once I know once I diagonalize the matrix and I know its eigenvalues and eigenvectors, there is two possibilities. The first possibility is that all the eigenvalues are distinct, which means all the eigenvectors are also easily determined. This is the one that we talked about in the last lecture. The second possibility is that some of the eigenvalues can be repeated. Again, this is something you should know, because once somebody says that I'm measuring observable A, then you should immediately know what the operator in quantum mechanics is and what the spectrum of this operator is. Okay, so let us say that you know that there is a degeneracy. Now, once you know this information, then this program works. Then the rule is that the way you compute the probability is by simply adding up the contributions from the overlap to the individual states. Okay, I will tell you a different way to think of this exact same thing in just 1 second. If this way of doing things confuses you a little bit, I'll talk about it in terms of projection operators. But to answer your question, you should know before you start calculating probabilities, you should know the matrix that corresponds to the operator, and you should know the eigenvalues and eigenvectors of this matrix. Okay, so the program assumes that you know A1, A2, A3 before you start, and you know that A2 and A3 are distinct or not distinct. Does that answer your question?
Yes, sir. Okay.
There is another question in the chat section. Do we find the probability of particles being in a state, or find the probability of particle having a given eigenvalue as you have done here? Probability of particles being in a state. No, the state vector. Okay, so this is a very tricky point. I know the state vector. Quantum mechanics is not a deterministic theory, because even though I know exactly what the state vector of a particle is, I still cannot say definitively before I do the experiment what would be the result of the experiment. I can only talk in terms of probabilities. But the evolution of the state vector itself is deterministic. Okay, Schrodinger equation is a deterministic equation. It tells me that if I know what psi is at time t equal to 0, I know exactly what psi is at time t equal to 25 seconds. Okay, there is no ambiguity there. There is no uncertainty there. There is no indeterminism there. It's a highly deterministic equation. But quantum mechanics is a probabilistic theory, even though the dynamical equation is a deterministic equation, because the rules for telling you what the associated outcomes of measurements are intrinsically probabilistic in nature. Okay, so the state itself, I know exactly what the state of the particle is. I can solve for the Schrodinger equation and figure out what the state of the particle is. But even if I know the state of the particle, I still cannot tell you with absolute precision what you would get prior to doing an experiment. That has to be an intrinsically probabilistic statement. Okay. Now, in the remaining 5 minutes, I will rephrase these probabilities in terms of projection operators for this exact same example, and hopefully you will understand it better. Okay. Now, I switched symbols, right? I wrote x1, x2, x3 as the eigenvectors, and here I have written 5, 1, 5, 2, 5, 3. I am sorry about that. But I will switch back. I'll stick with 5, 1, 5, 2, 5, 3. But notice that when I say 5, 1, 5, 1, that is the same as this matrix that we have written before, x1, x1, which is basically 1/3, 1, 1, 1, 1, 1, 1, 1, 1. Okay. Again, this is not working. Okay, so sorry about this. I've switched symbols. I should have written x1, x1, x2, x3, but I wrote 5, 1, 5, 2, 5, 3. But that's just notation. There is nothing deep going on here. Okay. All right. So, as you know, 5, 1, 5, 1, this outer product or this matrix is the projection operator. What is a projection operator? I'm sure by now, having solved the tutorial problems, you know very well what a projection operator is. It simply projects in that particular direction. In this case, this is an operator that projects in the direction of phi 1. So I'll call this P1 hat, which is basically phi 1, phi 1. Okay. Now, I can talk about P2 hat or P3 hat, but it is much more proficient for me to talk because both P2 hat and P3 hat project in the subspace, in the eigen subspace, which is given by constraint A, which is basically, I have to go far back and write it here. So both the projection operator corresponding to the direction phi 2 or x2 and the projection operator corresponding to direction phi 3 or x3, they both project into this two-dimensional space, which is given by the constraint equation alpha 1 plus alpha 2 plus alpha 3 equal to 0. Okay. So in other words, both projection operator 2 and projection operator 3 project into the eigen subspace. I will underline this. This word eigen subspace given by constraint A. Okay, which is basically alpha 1 plus alpha 2 plus alpha 3 equal to 0. In other words, the projection operator 1 projects in the direction of phi 1, and projection operator 2 and projection operator 3 both project into the eigen subspace into the two-dimensional space given by alpha 1 plus alpha 2 plus alpha 3 equal to 0. They both project in this plane. Okay. In other words, if I have a vector and I act P1 on that vector, then P1 picks out the component of that vector along direction 1. If I pick P2 or P3 on the vector, they both project the amount of the vector that lies in the plane given by alpha 1 plus alpha 2 plus alpha 3 equal to 0. So it makes sense to add these two and call a projection into the eigen subspace vector operator P2, 3, which is basically phi 2 plus phi 3. Okay. Now, let me reformulate what we have done before. So, what is the probability of finding A1? I'll write it in words. The probability of finding A1 is the modulus square of the overlap of psi with the direction of phi 1 mod square of this quantity, right? This is basically the probability. Now, what is the amount of psi that lies along phi 1? Well, that is simply given by p1 psi. Okay. So whatever this vector is, this is the amount of psi that lies in the direction of phi 1. If you don't believe me, let's evaluate this explicitly. What is P1? P1 is phi 1 psi, right? So this is basically the overlap phi 1 psi times the ket phi 1, which is what we've written here, the overlap phi 1 psi mod square. Okay, so that is what this is. So basically the probability of finding A1 is then this overlap, which is given by P1 psi, the norm of this quantity, P1 psi, P1 psi. Okay, this is the norm of this vector, where then vector P1 psi is the amount of psi along the direction of A1, along the direction of phi 1, excuse me, right? Now I can write this in a slightly different form if you want. Now notice that this norm is a basis independent statement. This is basis independent. Okay, if this confuses you, we will prove this in a tutorial problem. In other words, I can write psi in any basis, but the length of the vector does not change. The length of this vector P1 psi does not depend on the choice of the basis vectors. Okay. In fact, if you take an ordinary vector lying in a two-dimensional space xy, and if you rotate the vector, then the length of the vector is the same as before, right? X1 square plus y1 square will be the same as x1 prime square plus y1 prime square. That is the same statement we are making. The length of a vector is basis independent. So this is an important statement to make. And what will be P of A2? So I can write this in a slightly different form also if you want. So this is basically, since P1 is a Hermitian operator, I can write this as psi P1 hat psi. This is psi P1 square psi. But for any projection operator, as we proved in the tutorial problem yesterday, P1 square operator is the same as P1 operator. So this is the same as psi P1 psi. Okay. So these are all simple manipulations that you should be comfortable with. Again, the probability of finding it in this eigenvalue A2 is given by the amount of psi that lies in the eigen subspace alpha 1 plus alpha 2 plus alpha 3 equal to 0, because any vector that lies in this subspace has the eigenvalue -1, which is A2, right? So this is given by, just like the other one, the length of the vector P23 psi. Okay, which again can be written as psi P23 psi. Okay, so this is the norm of the vector P23 psi. Now, why is this important? Why is formulating the probability in this way important? It is important to answer this question, which one of you should have asked me. Remember that the probability is basically the overlap of the state vector with the eigenvector chosen, right? But the way we chose the eigenvector itself is very arbitrary in the case of degenerate spectrum. I could have chosen a different eigenvector that corresponds to the exact same eigenvalue -1. And then I could have picked another vector that is linearly independent of this guy. And those two would be perfectly orthogonal to each other. And I could have had two different vectors. Instead of x2 and x3, I could have had x2 prime and x3 prime that satisfied all these conditions that I wrote here. Where did I write them? Here. So conditions 1, 2, and 3. Okay, there was, for example, instead of starting with x2 vector equals 1, 1, minus 2, I could have started with x2 vector equal to 1, minus 2, 1. And then picked an x3 that is orthogonal and linearly independent to this vector. I would have had two different vectors. Now, when I compute the probability, since the eigenvectors are different, you can argue that now the probability should be different. So then there is a arbitrariness in this program. There should be no arbitrariness in this program, because the probabilities, which are experimentally measured quantity, should not depend on which eigenvector you choose. Okay, since in the case of degenerate spectrum, you are basically guessing the eigenvector. You could guess a different set of eigenvectors. So there is a natural confusion that can arise in your mind that maybe the probabilities would be different. But the probabilities will not be different, because if you view the probability of choosing an eigenvalue a1 or a2 as a norm of this vector, then the norm of a vector is a basis independent measurement, which means instead of choosing x2 vector and x3 vector that lie in the eigen subspace alpha 1 plus alpha 2 plus alpha 3 equal to 0, I could have chosen completely two different vectors that lie in the same eigen subspace, x2 prime and x3 prime. But if I compute the probability, this norm would still be the same. The norm of the vector p23 psi would still be the same, because norm is basis independent. Okay, so this factor is very important, and we will actually try and do a tutorial problem that demonstrates this to you. But again, as I specified in the case of rotations, you already know the answer that it should be basis independent, because if I rotate from x1 y1 to x2 y2, the length of the vector is conserved. That is, norm is basically the extension of the concept of length of the vector. Okay, so this is how you deal with a degenerate spectrum and the corresponding way you treat the postulate number 3 in quantum mechanics. Tomorrow we will move on to postulates number 4 and hopefully 5 also. And then once that is done, we will move on to the subject of function spaces.